ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. ನಾನು ಆದಿತ್ಯ ಅಂತ ಶೃಂಗೇರಿಯಿಂದ ಬಂದಿದ್ದೇನೆ. ನಾನಿವತ್ತು ಸೆಕೆಂಡ್ PUC ಒಂದು ಇಂಪಾರ್ಟೆಂಟ್ ಟಾಪಿಕ್ ಆದಂಥ ಮೂವಿಂಗ್ ಚಾರ್ಜಸ್ ಆ್ಯಂಡ್ ಮ್ಯಾಗ್ನೆಟಿಸಮ್ನ ಕಲಿಸ್ತಾ ಇದ್ದೇನೆ. ಮೂವಿಂಗ್ ಚಾರ್ಜಸ್ ಆ್ಯಂಡ್ ಮ್ಯಾಗ್ನೆಟಿಸಮ್ ಅನ್ನೋದು ಎಂಟ್ರೆನ್ಸ್ ಎಕ್ಸಾಮ್ಗಳ ದೃಷ್ಟಿಯಿಂದ ಬಹಳ ಇಂಪಾರ್ಟೆಂಟ್ ಚಾಪ್ಟರ್. ಸ್ವಲ್ಪ ಅದರ ಬೇಸಿಕ್ ಐಡಿಯಾಸ್ ಪಡ್ಕೊಂಡ್ರೆ ಈಸಿಯಾಗಿ ಸಾಲ್ವ್ ಮಾಡ್ಬೋದಾದ ಪ್ರಾಬ್ಲಮ್ಸ್ ಇರುತ್ತೆ ಇದರಲ್ಲಿ. ಈಗ ಅದರ ಬಗ್ಗೆ ಒಂದು ಇಂಟ್ರಡಕ್ಷನ್ ತಗೊಳ್ಳೋಣ. Until Oersted discovered that current carrying conductor produces magnetic field around it, nobody knew that electricity and magnetism were some linked phenomena. Everybody thought that electricity and magnetism were altogether different. Just after Oersted's discovery, many people like Ampere, Biot-Savart, Maxwell, Faraday, Henry and Lorentz discovered many other physical phenomena which are linked with electricity and magnetism. Today we shall study some ideas behind this magnetism. We shall calculate magnetic fields, we shall calculate magnetic moments, we shall calculate force between conductors, we shall calculate force on charges due to magnetic fields, and we shall study some magnetic fields of solenoid and toroid and etc. We know that a magnetic field is produced by either currents or changing electric fields. Suppose there is a charge q moving in a magnetic field. Let B be the magnetic field and B be the velocity with which the charge is moving, and let the angle between velocity and the magnetic field be theta. Then this charged particle q experiences a magnetic force due to this magnetic field when it is moves in the magnetic field. That is given by Fm is equal to QEB sin theta, where q is the charge, V is the velocity, B is the magnetic field and theta is the angle between velocity and magnetic field. Vectorially, this can be written as Fm is equal to q into V cross B. Here you can see that Fm is in the direction of V cross B, but V cross B is a vector which is perpendicular to both V and B. Therefore, magnetic force would be perpendicular to both velocity and magnetic field. Fm is both perpendicular to velocity and magnetic field, and this is a very special kind of force. Unlike electrical force, this force is a very special force. We can see here magnetic force depends on the orientation theta. Magnetic force is maximum when velocity is perpendicular to magnetic field, and that maximum force is given by q into V into B, because theta becomes 90 degree and sin theta becomes 1, and Fm magnetic force is 0 when either charge is 0. That is, if a neutron is moving in a magnetic field, it does not experience any force at all, because the charge on the neutron is 0. If the charge is at rest, that is, if the velocity of the charge is 0, then the magnetic force experienced by the charge is 0. That is, a stationary charge does not experience any force in a magnetic field. And if theta is 0 or 180 degree, that is, the angle between velocity and the magnetic field is either 0 or 180 degree, that is, the charge is moving either parallel or anti-parallel to the magnetic field, then also the magnetic force acting on the charge is 0. This is some idea behind magnetic force acting on a moving charge. Based on these ideas, let's solve some problems. Let us see the next question on magnetic force on a moving charge. A magnetic field in a region is given by B is equal to phi I cap plus j cap minus 2k cap. If the acceleration of the charge at an instant is 2I cap plus 4j cap plus ck cap, the value of C is. The options are A 3, B 7, C 28 and D 12. Now, I will use the fact that force on a moving charge is given by q into V cross B, which implies that force is always perpendicular to velocity and is always perpendicular to magnetic field. By Newton's second law, F is equal to ma, which implies that force and acceleration are parallel to each other. Therefore, if velocity and magnetic field are perpendicular to force, velocity and magnetic fields should also be perpendicular to the acceleration when the charge moves in a magnetic field. Therefore, acceleration is perpendicular to magnetic field when the charge moves in a magnetic field. If A is perpendicular to B magnetic field, then A dot B should be 0. We know that when two vectors are perpendicular to each other, the scalar product of those two vectors is 0. Therefore, A dot B equals 0, which implies A dot B is A is 2I cap plus 4j cap plus ck cap dot phi I cap plus j cap minus 2k cap is equal to 0, which implies you know how to evaluate dot products. I dot I is 1, I dot j is 0, I dot k is 0. Any unit vector when multiplied with itself gives you 1, any unit vector which multiplied by another orthogonal vector gives you 0. I will use that factor here. 2I cap dot phi j cap gives you 10, and this multiplication gives 0, this multiplication gives 0. So, no need to worry about it. Next, 4 into 1 is plus 4, the other two are 0, other two multiplications give you 0. Ck cap dot minus 2k cap is minus 2c is equal to 0, that give you 0. That gives us 2c equals 14, 10 plus 4 is 14, 2c gives you 14, which gives c is equal to 7. The value of c suitable for acceleration is 7. The option is B, 7. Now, let us see what is the nature of trajectory of a charged particle when it moves through a magnetic field. Here we have to consider 3 different cases. Here is the diagram which shows the velocity of the charge q moving in a magnetic field B. Theta is the angle between velocity and magnetic field. Depending on the value of theta, the path of the particle, the trajectory of the particle can be different. Suppose theta is equal to either 0 degree or 180 degree. We know that magnetic force acting on the charge is given by q v b sin theta. If theta is either 0 degree or 180 degree, then sin theta becomes 0. Therefore, magnetic force acting on the charge becomes 0. Then in such a case, there is no magnetic force acting on the charge. Therefore, the charge continues in its straight line path. The trajectory of the charge is a straight line when theta is either 0 or 180 degree. That is, when the velocity and the magnetic field are either parallel or anti-parallel to each other, the charge continues in its straight line path. What if, this is the first condition, let us consider the second condition. What if theta is equal to either 90 degree or 270 degree? That is, the magnetic field and the velocity are perpendicular to each other. What happens? In such a case, the charged particle undergoes a circular motion, uniform circular motion. We should remember one point here. The magnetic force, although accelerates the charge, it can never increase the velocity, can never decrease the velocity of charge. It cannot increase or decrease the velocity of the charge. That is, it cannot increase the kinetic energy or decrease the kinetic energy of charge. That is, magnetic force, although it can accelerate charges, it can never do work. It cannot do work. Now, when theta is 90 degree or 270 degree, the charge moves in a circular path, that is uniform circular motion with the constant velocity. The third case is theta other than these values, other than the above mentioned values. What if theta is some say 60 degree or 45 degree or 30 degree or 70 degree, so on? Then suppose the velocity is like this, the magnetic field is like this. The velocity, this velocity here can be resolved in two components. One is this one, the velocity, the component parallel to the magnetic field, and another is this one, the velocity perpendicular to the magnetic field. This component, as it is parallel to the magnetic field, does not feel any force, but this component, which is perpendicular to the magnetic field, experiences a force which gives you circular motion. Therefore, this one, the velocity parallel to magnetic field, gives you a straight line motion for the charge, whereas v perpendicular, velocity perpendicular to the magnetic field, sets the charge into circular motion. Therefore, a charged particle should have in this case both circular and straight line motion. Circular motion plus translation motion. The motion would be something like that. That's called either spiral motion or helical motion. Now, based on these ideas, let's solve the next problem. Charge with velocity v is equal to 3 I cap minus j cap plus k cap enters a region of uniform magnetic field B is equal to B naught I cap plus 4 j cap plus k cap. The nature of the path of the particle is, first option is a parabola, a helix, a straight line, a circle. Now, as we have discussed, the angle between velocity and the magnetic field decides the nature of the path. If theta, the angle between velocity and the magnetic field, is 0 degree or 180 degree, we get a straight line path. If theta turns out to be perpendicular, 90 degree, then the path is a circle. If theta is some angle other than 90 degree or 0 degree, then we get a helical nature. Let us calculate the angle between velocity and magnetic field so that we can decide the nature of the path. Velocity is 3 I cap minus j cap plus k cap, and magnetic field is given by B naught into I cap plus 4 j cap plus k cap. Finding angle between two vectors is easy. You can either use dot product or cross product. Using dot product is very easy. I use cos, I write theta is equal to cos inverse of vector A dot vector B divided by A B, that is a formula. That implies theta is equal to cos inverse vector A dot vector B is this vector dot this vector, that is 3 I cap minus j cap plus k cap dot B naught into I cap plus 4 j cap plus k cap divided by magnitude of vector A. Magnitude of vector, any vector, is square root of ax square plus ay square plus az square, that is square root of 3 square plus minus 1 square plus 1 square, that is 9 plus 1 plus 1, that is 11 into square root of b naught into 1 whole square plus 4 into b naught whole square plus 1 into b naught whole square. B naught is common everywhere, b naught I write here. 1 square is 1 plus 4 square is 16 plus 1 square is 1, square root of 18. Let us simplify this one. That is equal to cos inverse of this is 3 into 1 is 3 minus 1 into 4 is minus 4 plus 1 into 1 is plus 1 divided by b naught into square root of 11 into square root of 18, which is equal to cos inverse of 0, because this is 3 plus 1 4 minus 4, that is 0. Cos inverse of 0 is 90 degree. The angle between velocity and magnetic field turned out to be 90 degree, that is velocity is perpendicular to magnetic field, therefore the path of the particle has to be a circle. The answer is D, the path is a circle. The next point we will discuss is magnetic field due to a circular current loop. Let this be a circular current loop of radius r, current I and number of turns n. This is the axis of the circular current loop. Axis is a straight line which passes through the center of the current loop and is perpendicular to the plane of the loop. If I am calculating magnetic field here, I can calculate the magnetic field using Biot-Savart's law. The magnetic field here turns out to be mu naught n I r square divided by 2 into r square plus x square power 3 by 2, where x is the distance of the center of the circular loop from the point P at which we are calculating the magnetic field. As you can see here, as x increases, x is in the denominator, therefore magnetic field decreases. More the x, less is B. If point P come closer to the center, x decreases, therefore magnetic field increases. Then where is the magnetic field maximum? Magnetic field is maximum when x is 0, that is exactly point P comes on the center of the circle, that makes x equal 0, the magnetic field becomes 0. That gives us B is equal to mu naught n I r square divided by 2 into r square power 3 by 2, r square power x is 0, that gives me r cube, that is equal to, that implies B at center of a circular loop is equal to mu naught n I divided by 2r. As you can see here, magnetic field at the center of a current loop is directly proportional to the number of turns in the loop, is directly proportional to the current to the loop, and is inversely proportional to the radius of the loop. The direction of the magnetic field can be found out using right hand clasp rule. That says that if you curl your fingers with the fingers of your right hand such that your thumb is perpendicular to the curled fingers, if the curled fingers show the direction of the current, then the thumb gives you the direction of the magnetic field, implying that if you have an anti-clockwise current, you can also use right hand screw rule. You can keep a screw here, rotate the screw in anti-clockwise direction, this loosens the screw and screw comes towards you away from the board. The direction of the magnetic field is into. The right hand clasp rule also gives you the same direction. If the current is clockwise, then the screw goes in, that is the magnetic field is going in, the direction of magnetic field is into. This is how we find the direction of the magnetic field. Now let us see, what if we do not have a complete circle? As you can see here, we have a part of a circle, let the radius of the circle be r. If I draw two chords from the center to the extreme points that make an angle theta, what is the magnetic field at the center? Now I cannot use mu naught n I by 2r because it is not a complete circle. In this case, the magnetic field at the center is given by B is equal to mu naught n I into theta divided by 4 pi r. Magnetic field here is given by mu naught into number of turns into current into angle divided by 4 pi r. You should be very careful with this angle. This theta should be expressed in radians. That theta is expressed in radians. That is one point we have to remember. That becomes very important when you solve problems. The other point is that suppose you have a wire like this, it carries a current I. If you are somewhere here exactly straight, exactly in front of the wire, or somewhere here exactly behind the wire, the magnetic field here due to this wire is 0 and the magnetic field here due to this wire is 0. What is the magnetic field here is a different question, we will come back to it later on. But for now I am concentrating on this point. One is magnetic field due to a part of a circle, the other is what is the magnetic field exactly in front of a wire. Exactly in front of a wire, that magnetic field is 0, exactly behind a wire the magnetic field is 0. Let us solve some problems on the idea of magnetic field due to a circular coil we have learned just now. Here is the next problem. The magnetic field at point O in the figure is, here is the figure. Options are 11 mu naught I by 24 r, 7 mu naught I by 24 r, mu naught I by 6 r, mu naught I by 2 r. Here you can see you have a part of a circle and there is another circle here, they are connected through wires. This circle is not complete, almost 60 degree angle is cut, that's another part. Now, if this is 60 degree, when expressed in radians that becomes pi by 3, therefore, this angle must be 2 pi minus pi by 3, which is 5 pi by 3, 5 pi by 3. I will call this 1, this one is 3, this one is 2, and let me call this one 4. At this point, we are asked to calculate magnetic field here at O. As this point is exactly in front of this wire, the magnetic field due to this wire is 0. As this point is exactly in front of this wire or behind this wire, the magnetic field here is 0 due to this one. Therefore, third part and fourth part do not contribute anything to the magnetic field at O. What remains is to calculate the magnetic field due to this part here and that part here, then vectorially add them. Let us see what is the magnetic field due to the first part is B1 is equal to mu naught I theta divided by 4 pi r, that is the formula, mu naught I theta divided by 4 pi r, theta is 5 pi by 3, that is equal to mu naught I into 5, so 5 is here, 3 into 4 is 12 r, this pi get cancelled. That is the magnetic field due to this part, and the current is clockwise. If the current is clockwise, the magnetic field is directed into the board, therefore, the direction is into. Let us see what the magnetic field due to the second part is, this one, that is again mu naught I theta divided by 4 pi r, theta is pi by 3, the angle it makes is pi by 3, into radius is r plus r, the radius of this part is 2r, that is equal to pi get cancelled, mu naught I divided by 4 into 2 8, 8 into 3 24 r. This current is also clockwise, therefore, the direction of this magnetic field is also into the board. What is the net magnetic field? Net magnetic field, as they point in the same direction, these two point in the same direction and these two do not contribute anything, that should be, they should be added just because they are in the same direction, B1 plus B2, that is 5 mu naught I divided by 12 r plus mu naught I divided by 24 r, the LCM is 24 r, here I have to multiply with 2, 2 into 5 is 10 mu naught I plus mu naught I, that is 11 mu naught I. Therefore, the magnetic field here due to this part and this part, these two do not contribute, is 11 mu naught I by 24 r. The option is A, 11 mu naught I divided by 24 r. Now, next let us see the next problem on the circular coil. If R is the resistance of the coil in the figure, the magnetic field at O is, here is the figure. The options are A, mu naught V by 2 RA, mu naught V by RA, 3 mu naught V by 32 RA, and the option D is 0. Here is the circular coil. It is connected to a potential difference of V, battery of potential difference V. Here is the center of the coil, that is designated by O. The radius of the circular coil is A. As you can clearly see in the figure, this is 1/4 of the circle, this is 3/4 of the circle. If I call this 1 and this part 2, then length of first part should be equal to 3 times length of second part. That is 1/4 of a circle, 3/4 of a circle. This is 3/4 of a circle, that is 1/4 of a circle. Now, We know that resistance R is equal to resistivity into length divided by area. That is made of the same wire, therefore resistivity is same. That is a uniform wire, therefore area of cross section is same, therefore resistance is proportional to length. That implies, as the length is larger there, length is smaller here, length of resistance of the first part should be equal to 3 times the resistance of the second part. Here is the argument, resistance is proportional to length. But from Ohm's law, for a fixed potential difference, current is inversely proportional to resistance. For this one the potential difference is V, for that part also the potential difference is V, therefore the potential difference is same, therefore current should be inversely proportional to resistance, which implies that this condition gets reversed, that is I2 becomes equal to 3 I1. Therefore, the current flows here, if that is I, 3 times current flows here, that is 3 I current flows there. Now, let us calculate the magnetic field here due to this part, the magnetic field here due to the current flowing would be in this direction. Let us calculate the magnetic field here due to this part and let us vectorially add them. Let us calculate the magnetic field due to first part, B1 is equal to mu naught I theta divided by 4 pi r, but you know that you have 3/4 of a circle, therefore you have 3 mu naught I divided by 8 r, because mu naught I divided by 2 r is the field due to full circle, but you have 3/4 of a circle, therefore 3 mu naught I by 8 r. The direction of current is clockwise, therefore the direction of magnetic field is into. Let us calculate the magnetic field due to the second part, this one. You have 1/4 of a circle, therefore I should have mu naught I divided by 2 r into 1/4, that is mu naught I divided by 8 r. The current flowing through this wire is I1, therefore I should write I1 here. The current flowing through this part is I2, therefore I should write I2 here. That is equal to mu naught divided by 8 r into I2. What is I2? I2 is 3 times I1, which is equal to 3 mu naught I1 divided by 8 r. You may have noticed B1 and B2 are exactly same. The current in this loop is anticlockwise, therefore the direction of magnetic field is into. Therefore, B net, the net magnetic field at O should be B1 minus B2, because they are in opposite directions, but B1 equals B2, therefore I get 0. The net magnetic field at O is 0. The option is D, 0. Here it is not necessary that 3/4 and 1/4 of a circle to be connected. If you have a coil like this, one wire comes here, the other wire goes here, and they are connected to a battery like this. Even then the magnetic field here would be 0. You can argue that one, the magnetic field here would be 0, because although this is a smaller part, it carries a larger current, although this is a larger part, it carries a smaller current, and the direction the magnetic field produced will be opposite, they get cancelled each other, therefore the magnetic field here would be 0. Now, let us use the formula for the magnetic field due to a straight wire. Here I have an infinitely long straight wire carrying a current I. Suppose I am calculating magnetic field here at point P. Let the distance between these two be r. This point P is at a perpendicular distance of r from the wire. The magnetic field here would be B is equal to mu naught I divided by 2 pi r. This can be calculated using Ampere circuit law. The direction of the magnetic field is obtained using right hand clasp rule. Curl your fingers of your right hand and make your thumb perpendicular to the curled fingers. Now, if the thumb gives the direction of the current, then the curled fingers gives the direction of the magnetic field. That is how you find the magnetic field due to a straight wire. Now, this also becomes very important. What if we do not have a full wire, I mean infinitely long wire? What if we have a finite wire like this? Suppose we are calculating the magnetic field here somewhere, let the point be P. I can join this point and this point, and this is the perpendicular distance that I call R. Let this be theta 1, let this be theta 2. Then the magnetic field here at point P is given by B is equal to mu naught I divided by 4 pi R into sin theta 1 plus sin theta 2. Sometimes you may also have to use these angles. If this is phi 1, this is phi 2, from the figure you can see that theta 1 is 90 minus phi 1, theta 2 is 90 minus phi 2. Substituting that here, magnetic field here can also be written as mu naught I divided by 2 pi R into cos phi 1 plus cos phi 2. If you have a half infinite wire, I mean like this, that goes to infinity, but here it is cut. If I are calculating the magnetic field here at a distance R, then the magnetic field here is given by mu naught I divided by 4 pi R. Let us use these formulae to solve some problems. Now, we have to find the magnetic field here due to this 3/4 of a circle, this straight wire and this straight wire. Let me call this one part 1, let me call this part 2, and let me call this part 3. Part 1 carries a clockwise current, part 2 carries a current like this, and part 3 carries a current in the downward direction. This is 3/4 of a circle. Therefore, magnetic field due to first part is given by mu naught I divided by 2R into 3/4. Therefore, 3 mu naught I divided by 8R. I have multiplied mu naught I by 2R with 3 by 4. Next, I have to calculate magnetic field due to this straight wire. If I have a wire like this, if I am calculating magnetic field here, if I draw two lines like this, if this is theta 1, this is theta 2, magnetic field here is given by B is equal to mu naught I divided by 4 pi R into sin theta 1 plus sin theta 2. But here I have a wire like this, I have to calculate the magnetic field exactly below. Therefore, theta 1 becomes 0 and theta 2 is a diagonal to the circle. It has all the four sides equal, diagonal to a circle. This angle I need, that angle is 45 degree. Therefore, magnetic field due to second part, that is this one, is given by mu naught I divided by 4 pi R into sin theta 1 which is 0 plus sin theta 2 which is sin 45 degree which is 1 over root 2. Similarly, magnetic field due to third part, for which also theta 2 becomes 0, theta 1 is 45 degree. B3 magnetic field due to third part is given by mu naught I divided by 4 pi R into 1 over root 2 again. The direction of the magnetic field due to this wire, which is clockwise, is pointing inwards. By right hand clasp rule, the magnetic field due to this one is also pointing inwards. By right hand clasp rule, the magnetic field of this one is also pointing inwards. This magnetic field is pointing inwards into this magnetic field is pointing inwards. This is also pointing inwards. Therefore, net magnetic field at O is equal to B1 plus B2 plus B3. I add all of them because they are in the same direction. That gives me 3 mu naught I divided by 8R plus mu naught I divided by 4 pi R into 1 over root 2 this one, plus I add this one, they are exactly equal, therefore I multiply this with 2, that is B1, B2 plus B3 is 2 times B2. If I take mu naught I divided by 4R outside, I am left with 3 over 2 plus mu naught I by 4R in outside, 2 by root 2 is root 2 in the numerator, that is root 2 divided by pi. Therefore, the magnetic field here turns out to be mu naught I by 4R into 3 by 2 plus root 2 by pi. The option is D. D is the right answer.